All right. Hey, everyone. So welcome to discussion for today. It's day on November 9th. Yeah, I'm going to say 11/9. Yeah, it's discussion 11. So yeah, today we're talking about graph algorithms. So let's get into it. So we started about graphs last week, right? But today we're going to talk about a little bit more about graphs, right? Because maybe you're dealing with, instead of like we talked about last time, how you have weighted graphs, unweighted graphs. So this is going to be more related to how you can do things weighted this way, right? So we're going to start with shortest path algorithms. So it's going to be Dijkstra's algorithm for a single source shortest path and Bellman-Ford algorithm. And then when we have some time at the end, we're going to talk about minimum spanning trees, which is another graph algorithm. Okay. So shortest path algorithms. And so maybe you're thinking, okay, this is like the shortest path between one vertex and another. And if you're thinking that, you'd be right? Especially for a single source shortest path. It's for a single source to the other nodes or to a other node. Okay, so overview of shortest path algorithms is there's a single source shortest path problem. So this is where, and this is the one we're going to talk about today, is where you have you start with a single node in a graph and you want to find the shortest path to all other nodes. Right, in the graph, like you want to go ahead and find the shortest path to other nodes in the graph. Or to in the graph even. But for all pair shortest path problem, that's a little different. That would be the shortest path between any two nodes in the graph, for example. And yeah, or not any two, well, not just any two, but like all pairs of nodes rather, right? That would be all pairs, yeah. Like any two pairs of nodes, you want to find the shortest path between them. And one algorithm for this is Floyd-Warshall, which can handle negative weight edges and negative weight cycles, those cases, right? Negative weight edges and negative weight cycles. Other algorithms, there's some, I think Johnson's algorithm is another one for all pairs shortest path, but yeah, this can handle these cases pretty well, Floyd-Warshall can. But today we're just talking about single source shortest path. So in this problem, you have in the shortest path, you have a single source, right? For the single source one, you want to find the shortest path to all of the vertices in the graph. So for the unweighted case, it's pretty simple. We've actually already learned it, right? And that's BFS, because with the shortest path, right? Do you want to find the shortest path in an unweighted graph, right? That would be like, I'm starting here. Maybe I have a graph like this, right? It's just basically, you want to find the fewest number of nodes, right? To get to your destination, right? So, okay, or like how far does it take to get to here? Well, it's 1 to get to here, so 2 to get to here. And that's actually all BFS does. Like BFS just solves that problem exactly for us, right? Like we talked about BFS in the graph last week. But maybe you want something else, right? Like maybe you want it for a weighted graph. And for weighted graphs, it's actually kind of interesting because weighted graphs, we think of them as like the edges have weights. Maybe instead you could always think of it as having like extra nodes along the path. So that would be more weighted, but okay, I think having a weight makes more sense and actually makes sense for a problem better. Like, or it's a better, right? So rather than having like everything is distance 1 away from each other, maybe they're distance like k from each other. So what I'm trying to say is like in the unweighted version, right? We're basically, because all BFS does is it's basically just finding the distance. If you want to find the shortest path here, well, we're just using unweighted edges. So it's just edges of weight 1 basically, right? But here, maybe the edges have different weights. So for Dijkstra's algorithm, this is O of V squared time. So if you remember, V is the number of vertices, or if you want to do it with a heap, it's O of V plus E times O of V. So Dijkstra's, as we said, works the weighted graph, and just for the it does not work with negative weight edges. So yeah, so if there are no negative weight edges and it's a weighted graph and you want to find this single source shortest path, use Dijkstra's. But Bellman-Ford is a little more resistant because they can have, like edges can have negative weights and there's no negative cycles. Or like it can't work with negative cycles because nothing can, which we'll talk about, but it can detect these cycles. So that's pretty good. So let's get into these a little more. So first we're talking about Dijkstra's algorithm. So how does it work? Well, the idea is you have basically a table here of your start, right? You have all the different keys, so all the different like nodes in the graph, but you have your start one first, and the distance from the start to itself is 0, right? Because you're right there already, right? There's no need for it. This is going to be whether we visited or not, because so far at the very beginning, we haven't visited anything at all. As we said, the keys are the different nodes in the graph. Distance is okay. Distance, okay, is the distance from our start to, or like from S to that vertex. So of course it's 0 to get from itself. And we initialize those as infinity because we don't know if there's even a path there yet. So it just, we initialize them. And p sub k, that is the predecessor. So the predecessor of S doesn't have one, right? Because what comes before S in the path from S to S? Nothing, right? S is the first thing, so has nothing comes before it. But in general, we're going to keep all the things, we're going to keep track of what comes before. Okay, so this is how we kind of initialize it. We initialize it with this, and this is the graph we're going to look at. So what's the first thing we do? Well, let's see. The first thing we do is start with our first iteration. And what we do is we basically just like say, okay, what is S connected to, right? And it's connected to T and Y. So we say, okay, it's connected to T and Y, and these are like our candidate edges that we have so far. So maybe you can even think of, like if we're using a heap case, maybe we'd put edges into a heap and try and find the smallest. But what we have 10 and 5. And so 10 and 5 are our two candidates, right? But for what we're going to look at next. But the most important thing, because when we actually select S, what we do is we say, okay, S is our key, we already have that. But we say, okay, now we visited it. So when we visit it, we set this to true, which then allows us to do the following. We actually relax, that's the word we use, relax the distances to T and Y. So what that means is that we're going to say, okay, the distance to T, the shortest we've found so far of any path starting at S and going to T is 10. And the shortest path of any, the shortest path we found starting at Y, or starting at S and going to Y is 5 so far. And what's the predecessor? Well, it's the path along which we found the shortest distance. Like what came right before it in that path? Well, S, right? Because S comes right before Y and comes right before T in these. So the predecessor of T and Y so far is S. But now the next thing we're going to do, right, is so far we only have one node as part of our solution. But what you might notice is that because dextrose does not have negative weights, edge weights. Actually, wait, we'll move on. We'll talk about that in a second. Okay. So now we'll talk about it. So the next thing we do is we actually choose the shortest, right? We choose the smallest edge weight. And the reason why we're able to do that and say, okay, now that's the next thing we're going to include. And the reason why we can do that is because there are no negative edge weights. Because what we know is when we choose Y, right, there can never be, no matter what else we relax, right, there can never be any other path starting at S and going to Y that's going to be less than weight 5. Because so far, the smallest weights we've seen, right, are 10 and 5. So the only way, because we have to start at S, right? We have to start at S. The only way we can ever get back to Y is either we go through this path, this one right here that has the 10 on it, and there's some other path in the graph that winds up at Y. Well, there are no negative edge weights, right? So no matter what path we take, it's going to be more than 10 or 10 or more, right? So that's obviously not less than 5. So of course we're going to want to choose the smallest. So that's not it. But if we go to Y, right, and then when we take some other path in the graph and then back to Y, it can't be less than 5 because there are no negative edge weights. So basically what this tells us is how we're choosing them is good, right? Because we're able to choose the smallest at each point in time, because when we choose the smallest, there can't be a smaller because there's no way to decrease on any path back to it, right? So that's kind of the intuition. Hopefully that kind of makes sense why we're choosing the 5 right now. And we know it's going to be the shortest no matter what. It's going to be the shortest because there is no other way. Like if it's the shortest so far, there are no negative edge weights. So of course it's the shortest by the end, right? So that's the intuition part. But okay, Hopefully that makes sense. And so what we do is we're like, okay, our candidates were 10 and 5, right? So we chose the smallest candidate because that one has to be part of the solution. Yeah, it has to be the shortest path from S to Y. So what that means is now, okay, Y has now been visited, right? We're now going to say, okay, Y is visited. And when Y is visited, we say, okay, basically this is part of solution, distance was 5, and its predecessor now we know for sure was this. But when we visit something, what's the next thing we do? What's the next thing we did before when we visited S? We look at its neighbors, right? And we relax the edges. So now when we do a relaxation, we do the relaxation on Y because we've already relaxed everything on S. So there's nothing else to relax on S. So there's only one node left that where it is even worth relaxing because we only relax visit nodes edges. So, or out edges, right? Okay, so now we look at Y. So we're going to relax this one. We're going to relax this one. And we're going to relax this one, right? And when we do that, we're actually going to go to the next slide so we can see what it looks like. So yeah, these are the ones we relaxed. And if you notice, we actually had some updates. So of course, these were updated from infinity because these are less than infinity. And the predecessor so far is Y because the path that goes through Y last, or like most recently through Y, is shorter than any other path, like to get to Z or to get to X. And the way we compute this distance is we actually add. We know it takes 5 to get to Y, so it takes 9 plus 5 to get to X, and that's less than infinity, so that's the shortest path. But also interestingly, remember how we had the shortest before to get to T was 10. Well, now it's only 8 because it's 5 and 3. So now we have that the shortest path to get to T is only 8. So we actually update it. And we also update the predecessor because the predecessor in the shortest path, right? The last thing along the path was Y, not S, right? Because we have to go S to Y to T. So now that we've done this, what's our next step? Maybe you can think about it. Okay, yeah. So you could have paused if you wanted to, just can, but trying to think. But the answer is the next thing we're going to do is we have to, after we've relaxed the edges, we choose the smallest distance here. What's the smallest distance? It's this one, right? So the next thing we're going to do is we're going to visit Z. Yeah, so as you said, as we see, distances are relaxed. Okay, so yeah, next thing we do is we visit Z. Mark it as visited and say, okay, here we're marking it as green, right? It's green, part of the actual solution. When we do this, like, okay, now we need to do what? Relax the edges on Z. So we do that. What are the edges? Well, this one and this one, right? And the good thing is remember, because we know that anything visited is already part of a solution, even if there's a path from Z to S, we already know S is part of our solution, so we don't even need to actually like check it. I mean, we'll check the edge, but like we don't really need to compare because if it's already part of our solution, this can't be shorter to get to S. And I mean, of course it can't, right? Because it's 0. So next thing we're gonna do is we're gonna relax the edges. So we'll see the update here. Yeah, this since X is relaxed. And as we see, we don't, like, as we see in the description here, we don't need to relax the edge to S because that edge cannot be part of any of the shortest paths. So we relax the edge to X, and we notice it actually decrements or decreases, right? It decreases the distance so far. So it decreases 13, so now its predecessor is Z. But we also, we don't have any effect on this one because there's no edge from Z. So what's our next step? We choose among the ones that have not been visited so far, the smallest distance. Okay, so we choose one smallest distance, and well, that's 8, right? And that's T, which is distance 8. So that becomes our part of our solution, and its predecessor is Y. And then we relax its edges as well. So we relax its edges. Again, Y is visited, so don't really worry about, relaxing that, but we relax X. We actually notice it makes it shorter. So its predecessor, X's predecessor becomes T. So now we visit X and we're done. And we also mentioned, right, the fact that Dijkstra's doesn't work with negative edge weights at all. Or it doesn't work with negative edge weights. And we kind of went through that, right? It doesn't work with negative edge weights because we were kind of relying on the fact that it doesn't have negative edge weights to choose something as part of our visited at any point in time, right? like we were saying, oh yeah, there can't be any other way to get them. Yeah, but that's just mentioning something. But yeah, after the 5th iteration, right, we visited everything, so we're done. So that what we know now is the shortest path to get from S to T, for example, is 8. From S to Y is 5, S to X is 9, and S to Z is 7. We can actually reconstruct the path too, but we'll get to that in a minute. So the idea of edge relaxation, which we were doing, right, is we consider an edge and whether the path through the vertex U to B, like any two vertices, right, is better than any of the previous paths. And if it is, we both update the distance for that key, right, V, and we update the predecessor, right? So basically, it's for the edge from vertex U to B, if du plus the weight of, or yeah, the distance to U plus the weight of that edge is less than the current distance we have to V, then we update the distance to V as that, right? Because if there is a path, like if there's a path in the graph that has that's shorter, right, to get to V after relaxation, right, then we update what that path was, right? Because there was a longer path originally, or maybe no path at all to get to V. So now that we know there exists one and it's shorter, right, we update it. Okay, we say, okay, that's our shortest because to get to V so far, because it's shorter than anything we found so far. Right? So there you go. Yeah, and the algorithms for the shortest path problem solve the problem by repeatedly using edge relaxation in a certain order. And we'll actually notice that edge relaxation is a really common thing to use, and we'll actually use it again with Bowman fourth. But before we get to that, let's talk a little more about dextrose. So for dextrose, it works with a weighted graph and no negative weight edges. And it works with directed and undirected graphs. And it runs in O of V squared time, or if you implemented a heap and adjacency list, it's O of V plus E times log V. And yeah, we determine the shortest path to each vertex from a single source. Because a single source shortest path algorithm is a greedy algorithm. What we mean by greedy is that it just chooses greedily, right? Like there's some greedy nature to it. Like it always like does the same thing. Like it doesn't really consider options. Like here, what I mean by greedy is like every single time, the thing we chose to be part of our solution was the smallest distance we hadn't chosen yet. So that's what I mean by greedy. There's some approach it always takes, it always chooses like the smallest thing in order to get as part of the solution in order to get to the solution. If we wanted to choose which one do we want to mark as visited next, we always choose the smallest, right? So it's a greedy approach. Yeah, and choose the next vertex visit, which has minimum distance of all the vertices you haven't seen so far, or you haven't visited so far. And in each iteration, we apply the relaxation principle to all the edges, and yeah, that's it. And that's kind of how we go through the extras. Okay, so what's next? Well, next thing is poll question, which is the following is not correct about dextrose. You can pause and try and answer it. All right, so now we're gonna go over it. So let's see the answers. So is it a greedy? Does it use a greedy strategy? Yes, it does, right? It always chooses the shortest or the smallest edge weight to include as part of the solution. The input graph can have negative weight cycle or negative weight edges. It can't have that, right? We discussed that it can't. It's a single source shortest path algorithm. Yeah, absolutely. And the input graph can be undirected or directed. And that's also true. So it's only the second one. Okay, so let's, yeah. So we covered the variation of it, or the variant of it, maintains 3 maps. So map 1 is a map that tracks whether you visited it or not. So for that, you can use something like a set, but maps is fun. Each vertex is a key, and then a Boolean value is used to whether vertex has been visited or not. So it's basically just like a set, but a map is also fine. So you map like vertex whether it's been visited. You have distance. So basically, you have a map which stores distances from the source node. So each vertex is again a key, and the distance you initialize as infinity, but what it maps to is the distance value. And the source vertex's distance value is set to 0, right? So that way we always choose it first, which makes sense, right? That's how we make sure, because we're always choosing the smallest. So we set all of them infinity and one of them 0, we're going to choose 0, 1 first. So predecessor map. So this is how we keep track of the predecessor. So each vertex is a key, its predecessor is the value, and the predecessor is the thing that we got to, like we visited right before we visited this one. Like the path, whichever path we took, whatever we visited right before it, to get there is its predecessor. And all values are initialized as null because we haven't visited anything before our current entity. And that's how we determine the shortest path. So this is how we reconstruct what the path was, rather than just the length of the path. So, okay. This is kind of the approach. We initialize V, our map, with all vertices marked as unvisited, distance with the source vertex value set to 0, and all the rest are set to infinity, right? And P has all values set to null. And then while V has an unvisited vertex, find an unvisited vertex U. So you find some vertex U that has the minimum distance, volume, distance. This step is why you'd want to use the heap or priority queue. And that's why when we discussed earlier possible approaches, that's why we always mention the priority queues an option, because this is exactly why you'd use them. Is because if you want to get the minimum, right, out of a set of things, like the way you do that, if you want to do that repeatedly, like a pretty efficient way of doing that is to use priority queue or heap. And then you mark U has been visited in V. And then for all of its edges, you want to do the relaxation. The way we do that is if Y is not visited yet, you relax. And relaxing involves selecting the minimum between its current distance and the distance to get to the node we're currently at, plus its edge weight to that other node. And if it was less, then we update its predecessor, like the neighbor's predecessor, right, to our current node. So what does the code look like? It's something like this. Again, we have an empty set at first, and then while we haven't visited everything, right? We haven't visited all the vertices, we keep extracting the minimum distance, and we include the new vertex in our set of visited vertices. And for each vertex, which is adjacent to it, we relax. So we relax the edges. That's the idea. So question number 2. This one we haven't gone over yet, but hopefully maybe you can see something kind of intuitive about it. And if not, then, I mean, either way, we're going to go over it. But how would you just figure out, using the predecessors, what nodes are on, like what is the shortest path from S to X? All right, so we're going to go over it. You can pause if you want though first. Okay. So why don't we start at X actually? Well, let's work backwards, right? So remember, it was single source. So we know all of these are the shortest path from S. So we start at X. What was its predecessor? T. What was T's predecessor? Y. What was Y's predecessor? S. So what we know is that the last thing was X. The thing right before it was T. The thing right before T, right, was Y. And the thing right before Y was S. So the path went S, Y, T, X, and that is 1. That's what we figured out. And so that's our answer. Right? Okay. So now, how we do with this one, how would we find the shortest distance between S and X? All right. So you can pause if you want. Now we're going to go over it. The shortest distance between S and X. Well, here we look down at the key, and we actually just look at this distance, and that's it. It's just 9. There's nothing more to it than that. And the reason why is because, remember, as we went along throughout the algorithm, we were keeping track of like the sum of what the weight was to get to the current node, and then we were adding on, right, the weight of the edge to the next node. So at each of these DKs, right, or Ds of Ks, those are just the weights to get from the source to that vertex. So from source S to X, it's just 9. Okay. All right. So that covers these 4 questions. Oh yeah. Oh, actually, there's one more. Yeah. Or maybe a couple more. But yeah, given the following graph with W as the source vertex, what will be the distance values in alphabetic order after the second iteration of Dijkstra's? Well, let's try doing 2 iterations of Dijkstra's. So in the first iteration, right, Well, notice like W, we visit W, relaxes edges, right? So when we do that, it looks like this. And you can always pause if you want. But yeah, we relax its edges, and then we choose the minimum. Well, the minimum distance is 5. So then we choose that as part of our solution, and then relax its edges. And we relax its edges, we're going to get 0, 8, 5, and 7. Okay. So for this, we just walked through the relaxation just like we did earlier. So I'm not going to go into as much detail as that. It's the same idea. Like you just choose something, you choose your source beginning, set it to 0, mark that as visited, and then you relax its edges. And then of the smallest vertices, like smallest distance k's, right? Choose the very smallest one, mark that as visited, and relax its edges. And you keep going. And that's it. And eventually you're just done. But here we stop after 2 iterations. So we just have to see. Okay. But what do we do if we have negative edge weights? Dexters won't work. Because of us choosing greedily, dexters is not going to work, right? It's the problem that we talked about earlier. And it's really not going to work with negative edge weight cycles either, because it requires negative edge weights to have a cycle of negative weight. So, okay, doesn't work for either. And we can see why. Let's see why. So let's say we start at S, right? And then we go to Y because it's the smallest. And then we go to T because it's the next smallest. And then now what? Well, now we would think we're done, but not really, because there's a shorter path. There's a shorter path, and the path is from S to Y, then 2, it's negative 5. And there's a shorter path from S to itself, then 0, it's negative 3, and so on. And like, that's a problem, right? And this is a negative edge weight cycle, but even without the cycle, it's still a problem, right? Because we're still gonna have to update Y after we've already visited it. But the idea is, with dextrose, once you visited, you don't update. You don't have to relax again on anything that goes towards it. So that means that dextrose doesn't work if they're negative edge weights. So we need something else. But here we have a negative weight cycle. And it also includes a negative weight edge, but it also is a cycle. And so, yeah, here it's better to think of cost rather than distance, because like maybe it's hard to understand where distance will come into play with negative. But yeah, as we said, right, it costs negative 3 to go all the way around the cycle. So just keep taking the cycle, and it's less and less and less cost. So there is no shortest path, but we would need to know that somehow. So how do we identify that? Well, okay, that's what Bowman-Ford is for. Bowman-Ford's algorithm actually does work with negative edge weights. And obviously negative edge weight cycles, like we just mentioned, there's no shortest path from anything to anything, because we can just keep taking the cycle and get less and less cost. So rather than doing that, because negative edge weight cycles just never work. So our negative weight cycles never work. So Bowman-Ford will identify when that happens for us. Like that's what this algorithm, one of the things this algorithm is used for is to detect negative weight cycles. And it can also handle negative edge weights, which is nice. It's similar in a lot of ways to dextrose, but there's some difference. So it's a little bit slower. It's O of B times E and more complex, but it's more versatile than dextrose because it handles these cases. So let's talk about it. So the real difference, right, is that at each iteration, rather than just relaxing the edges on visited edges, right, it relaxes all edges on all of the new vertices we're visiting. And it performs exactly V iterations, right? And what that means is that we're going to do V minus 1 iterations to find the optimal distances. And so at the ith iteration, we're going to relax any new edges we haven't relaxed already. And then at the last iteration, we reveal, like we do V minus 1 iterations to find the values. And at the Vth iteration, the exact last one, that's when we detect whether it's a negative weight cycle. And the way we're going to do that is basically if we keep improving, like if the cycle, like if the graph, we're able to reduce edge weights, even on the Vth iteration, there has to be a cycle. Okay. And yeah, or not just a cycle, but a negative edge weight cycle, which is not good. So the order in which you relax the edges, it can affect the performance. And so that's something to keep in mind. It's like it can affect the performance, how you relax them, but it won't affect the results. So let's look at how it works, right? So originally we initialize our map, and again, we're using a map, a few maps, right? Is we have V, which is our vertices, G sub V is our distances, and P sub V, again, these are predecessors. And so we initialize them, and here we have V equals 3 iterations. And this is how we're going to identify. Here we can actually see we're going to identify that there's a negative weight cycle. And so the very first thing we do is, in the first iteration, we're going to start with edge ty. And, well, we notice that ty is a problem. That's one of the edges. And what we're going to first do is we're going to relax, right? We're going to start at S, we're going to relax the edges in the first iteration. And what we notice, right, at each iteration, we relax all the edges, right? So we try to relax ty, but from t to y, that's infinity to infinity. It's not going to work, not going to do anything. Then we relax s to t. And what this is going to do is it's going to choose s to t, right, as shorter than infinity. So it sets predecessor of t to s, and then s to y is going to set predecessor of y to s, and it's going to update distances. Then we do another iteration, so we do a second iteration. The second iteration, we're actually going to update this way, right? And so negative 10. So this becomes negative 5 because it goes from 5 to negative 5, or 2 to negative 5, right? Because 5 minus 10, negative 5, that's better. And then 5, so we update this one. Still 5 is best because 0, 5, same. And then 2 here, right? So now we do a final iteration. And 2 is not better than negative 5, so we leave it like that. So that's the end of our second iteration. So now we start our third iteration. And again, this is should have no updates. If there is an update, that must mean that there's a negative weight cycle. So we're actually going to check, is there an update? Well, not so far, right? Well, here, right? Here, yeah, there should be no updates. And here, we actually don't see an update, right? So what this means is that there is no negative weight cycle. So I think, yeah, it looks like it at first, right? But this is actually not a cycle because it goes in this direction. So yeah, this works with negative edge weights, but there's no cycle here. Okay. So there should not be a relaxation, and we don't notice relaxation. So that's a good thing. And so we'll talk about pseudocode in a second. But the main idea of Bellman-Ford is basically at each and every pass or every iteration, we update all of the edges, or we try and relax all the edges, or we try and update. We go through all the edges and try and update the distances, and then update the predecessors based on that. But the thing is that since we go through all the edges, right, at each iteration, at each of the v-1 iterations, right, since originally we already have our source vertex as part of our solution, at each of the iterations, what we would expect is that for one of the edges to include a new vertex in our solution, right? And if, for example, something like this, right? Let's say that this one was actually this edge too. Then what we'd expect is that each time we actually have something new included in our solution. So we would expect, for example, in the first pass, maybe we expect T to be part of the solution. In each pass, there's always going to be something new part of your solution. But if there's a negative edge weight or a negative cycle, right, then no matter how many times you go, you're going to have improvements. But since at each pass, we're expecting something new, some new vertex should be part of our solution. I mean, by the end, the only way that now we have identified, after v-1 iterations, we've identified the different vertices that it should be part of our solution. But if we keep updating, that must mean that one of them gets updated again. And if it's updated again, right, even after we've identified everything in the cycle or everything in the graph, then that must mean that there's some way to get from there back to itself with negative weight. So maybe that makes some sense, but yeah, it's kind of the idea anyway. But yeah, that's kind of some intuition for it, but maybe that's not quite as important. I just wanted for you to get an idea of what's going on. But again, the main idea of Bellman-Ford is, in this graph, for example, it's similar to Dijkstra's in that you have a predecessor array, distances array, and vertices array. But every time you update, you look at all the edges. rather than just looking at the one of the new vertex that you just included in the solution. Okay, so yeah. So step one is to initialize the graph and map for the distances and predecessors. Just as with Dijkstra's, similar so far. The step two is you relax edges repeatedly. So v minus 1 times, you're going to try and relax all the edges in the entire graph. And then step three is you make one pass in which you look at all the edges in the graph. And if the distance u plus distance v for any of them, right? If for any of them you actually still make another update, there has to be a negative weight cycle. And so it fails. And that's how we know that. And that's a good thing that we can identify. So that's the idea of Bellman-Ford. Okay, question number 5. Bellman-Ford is able to find the shortest path in any graph with negative edge weights. I'll pause and try and answer it. And so the answer is false, right? Because it identifies if there is a negative weight cycle, which is great. But if there's a negative weight cycle, there is no shortest path in the graph, right? So it can't identify because there isn't one. Yeah. Okay, true or false, or not, that was true or false. Next one, minimum number of iterations, which it could converge to its ultimate solution. So after which iteration is it possible that there are no further updates to the distance round? Okay, so you can try and answer. And so if the answer for this one is actually 1. And you might be surprised, right? It might seem like v minus 1 at first, but it's not, because even going back to this example here, notice in the very first pass we made, first iteration, we actually updated them all. Okay, we updated them actually in the second iteration. But let's say that in this graph, this were like, I don't know, 100, right? Then we would have been done. We would have identified 5 and 2 after the first iteration. And no matter how many more iterations we made, it wouldn't have mattered, right? So you can identify after the first iteration. Let's go forward again. You can identify after the first iteration. Or you can't identify after the first iteration. You can be done after the first iteration with updates. But you can't identify, sorry, I was using the wrong word. You can't identify if you exit early, because there's no way to check that, right? You actually have to go through all of them and forward, because for all we know, there's still a negative weight cycle. So we actually have to go through v minus 1 iterations. But it's possible after just one iteration, you've found what will be the ultimate optimal solution. Okay, so what real-world problem would be a better fit using Bellman-Ford than Dijkstra? Okay, so you pause, and we can try and get through it. Okay, let's go through it. Is the shortest drive from Miami to Seattle? That's the shortest path. That's single source shortest path. And so that sounds a lot like either would work, but for something like that, Dijkstra is faster, so we would not prefer Bellman-Ford. Cheapest drive. Well, here, rather than thinking about the weights as distances, we can think of the weights as the cost from point A to point B. And again, we can still build a graph with it. So that's not really it either. Hottest drive from Miami to Seattle. Maybe now, again, we think about the temperatures, right? And temperatures, for hot temperatures, we expect positive numbers. And so again, positive numbers, still better off using Dijkstra's. The coldest drive, we might have negative numbers. So for something like this, Bellman-Ford seems like the good approach to use. And hottest drive maybe requires longest, which is, yeah, a different set of problems altogether. Okay, successful question number 7. So that's it for Bellman-Ford and Dijkstra's. Hopefully that made sense. If you have any questions about them, of course, message me. But next, we're going to move on to the next set of algorithms, which is actually talking about the extra material, but minimum spanning trees. So minimum spanning trees are kind of interesting. And okay, first we're going to talk about taking cycles union find data structure. So what is union find? Well, union find is a data structure in which you're able to actually, you have basically a set of things, and you have 3 different operations: make, set, union, and find set. So if something doesn't exist in any set yet, right? If it's not in any of the sets, then you make the set, and it only contains self-contained. For union, you union two sets together, and for find, you try and identify which set that thing exists in. And this is actually really helpful for one of the algorithms we're going to help in a second. And it's really interesting because like union and find is actually a data structure itself, but it's used in algorithms sometimes, so it's pretty cool. And it tries almost to how to put this? It's almost like it acts almost like a tree structure in that the way it actually unions things together allows you to then do a find in log of the number of things in that set time, rather than having to search them all. And that's the beauty of the union find algorithm or data structure, is that it's really good at finding which set something belongs to. And then making set is pretty much instantaneous, and union is also relatively fast. So that's something about the union and find. Maybe it's not clear why we would want that yet, but we'll talk about an algorithm in a minute. The second one we'll talk about for the MST problem, the spanning tree problem, that actually uses union find. But anyway, for make set, yeah, you set the rank to 0, you set the predecessor to X itself, right? And then for union, you're basically just doing the linking together the find set of X and the find set of Y. And then we can put a link here too, right? A link is, you basically choose the one of larger rank and make it the predecessor of the other one. But if they're equal, then if they're equal, then you increment the rank of one of them and then make the other one like child. And then for find set, you're just checking if, making sure X is not its own predecessor, and if it's not, then you find the set that its predecessor belongs to. And yeah, that's about it. And ideally, this going along this path, right, shouldn't contain all the nodes. Because if you think about it, when we're actually creating them, right, let's say this is X, right, we have a Y. Well, maybe there are other nodes that we put in here. Maybe they're added to X and Y, or maybe they're added to something else. That way, when you union together X and Y, we have the larger one first, let's say X is larger. But then Y will be like another child of it. So hopefully we don't have to go through all of the things. We only have to go through some. And so on average, maybe we're expecting something like log of it. So it's almost like a tree structure. So that's kind of cool. Okay. But anyway, this is the idea of union find. And we'll talk about why it's important soon. So the reason why is because we need it for one of the minimum spanning tree algorithms. So minimum spanning tree, or MST, the idea of it is it's a subset of edges of a graph for connected, weighted, and undirected graphs specifically. There are other problems that are very similar for like directed, but minimum spanning tree in general is connected, weighted, and undirected, in which you connect all the vertices together. So you want to basically find the minimum cost, minimum cost to basically just have a connected graph, right? So minimum cost graph, which includes all the vertices, and it connects all the vertices together, and it's without any cycles. This is not a necessary condition, because in general, for minimum spanning tree, we talk about minimum spanning tree usually. Okay, well, it's a necessary condition here if we're not talking about negative edge weights, but in general, we assume, or usually for minimum spanning tree, usually we consider it with only positive edge weights, like in this case here. So for this case, it wouldn't matter whether we mention cycles or not. But yeah, I guess for the general case, right, it doesn't have any cycles. Is something we would mention. But if it's all positive edge weights, then we don't have to mention it, right? Because the smallest weight, if we just add extra ones, it would cause more trouble. It would cost more. So anyway, so the idea is, yeah, we don't have any cycles. We connect all the vertices together, and it's the minimum possible total edge weight. So two famous algorithms are prims and crystals. And for crystals, we're going to talk about why we need union find. Prims, we don't. So we're going to talk about prims first. But they're both greedy algorithms. And MST graph is not necessarily unique. It's unique only if the edge weight's unique, right? Because otherwise, like, I don't know, if there's like a 4 here, and maybe, let's say for example, if all the edge weights were 1 even, right, then we could choose any subset of them that gets all of them. So like this, for example, if it's something like this, the best minimum spanning tree, if these are all 1, could include just these edges, like these 2 edges, and excluding this one, or we could exclude this one, right? But either way, it's the same. But if they're all unique weights, then if all the edge weights are unique, then there is a unique MST. But okay, let's talk about prims. So what is prims? So prims, the idea is you have 2 sets that you're dealing with, 2 sets. And the sets are the set of, you have 2 sets of vertices. Vertices which are part of your solution so far, your minimum spanning tree so far, and vertices which are not part of your minimum spanning tree so far. So it's kind of like, if you remember with Dijkstra's, what we were talking about was, over time, we choose a new vertex to include as part of our solution when we mark it as visited. But here with prims, we're choosing a new vertex to include, right, as part of our solution. And when we do that, it's removed from the other set. And yeah, so given a connected weighted and graph, prims results in a minimum spanning tree. The time complexity is OD squared. And the adjacency list, if you use the adjacency list plus a heap, again, I think a heap makes sense for this. It's E times log V. Maybe you can kind of see after we're done talking about it, why you might want to use heap or where you might want to use heap. But the idea is, we'll talk about pseudocode. You create an empty set, you put an arbitrary node in the set, and while your set does not contain all of the vertices of the graph, right? Because we have 2 sets, the set which has, which is the MST, and the one that's not the MST. And while your set does not contain all vertices of the graph, you add an adjacent vertex with at least the edge weight, with the least edge weight, right? The smallest one, and if it's not in the set already. So basically, every single time we're going to choose some vertex which we haven't picked already, right? So every single time we choose the vertex which we haven't chosen already as part of our solution that has the least weight. So basically, we have all of our vertices, right? It doesn't contain all the vertices. So maybe at some point in time we have, okay, we'll go through an example in a minute, I think. Yeah, here we'll go through an example. So originally we create a set of MST vertices. So you pick any vertex because every vertex is going to have to be part of your solution. So at random, doesn't matter. You can choose any vertex you want and add it to your set. When we do this, our set is just A. And notice everything else, right, is part of our other set, which is not part of the MST yet. Right? But the next thing we do is we actually say, okay, well, our set doesn't contain all of the vertices, add an adjacent vertex with the least edge weight, which is not in the set already. So basically, like, okay, C and B are not part of it, and the edge weights of them are 1 and 6. So we're going to choose this 1. We're going to choose B, right? B is now going to be part of our set, and everything else is still not part of our set. So basically, we choose the edge. We choose the vertex which has we choose the edge basically, because we know all the vertices are going to be part of our solution. So the edge that we're basically only choosing edges that we want as part of our solution in the end. The end result is to choose the edges, right? Because we know all vertices have to be there. That's by definition minimum spanning tree. So we're choosing the edge which crosses the gap between some visited and unvisited, basically, or part of our solution and not part of our solution. Something that bridges the gap between those 2 sets. And then we now visit that, or we might now put that edge in our set, and we put that vertex in the set of vertices that we include, right? Okay. So adjacent vertices are B and C. B's edge is the least weighted, so we add that to our set. And again, here's where you might think, okay, here's where we keep priority queue. So we want to know, how would we possibly know what the smallest edge weight is out of all the ones that we can possibly pick? And that's why we use a priority queue. We put everything into the priority queue or heap. So that's why we mentioned the heap as an option here, because of exactly that. So heap is a nice way. It's kind of cool. We're using data structure to talk about. Okay, but anyway, what's next? So then we pick B, right? And now we have to choose. Now now 6, 4, and 7, for example, might go in our heap, right? Now we want to choose the edge weight of least cost. And again, we're not worried about the shortest path. We're worried about the smallest weights. So we don't have to like add 1 plus 4 because it's just 4, right? Because we want the smallest combined sum of the edges, not any path. So here, because we chose A arbitrarily, there's no source here really. So now we have C as part of it because this one is the smallest, 4. So we choose C. So A, B, C. And then we're going to look at C's neighbors. Now we're going to say, okay, now we add 9 to our heap. Then we remove the smallest from our heap again. Oh, look, the smallest is maybe either C or D. And then we keep going. And so then, yeah, we choose D because 6 is the smallest, right? Oh, wait, sorry. I mentioned that we would choose C. We would not ever choose this. We would not ever choose this because we already have C as part of our solution. And this would create a cycle. We don't need a cycle. That would just not be part of our minimum spanning tree. Wouldn't be a tree, right? So we choose the 6 here. Or sorry, we don't choose the 6, we choose the 4. I missed that the 4 was an option here. Yeah, so 4 is also part of our heap. 6 is the last thing we'll choose. So sorry, I was getting ahead of myself. We would choose the 4 next, and we choose the 4 next because 4 is the smallest remaining. So yeah, adjacent vertices are D and E. D's edge to B is the least weighted, so is our set. And to remember, at any point in time, and the reason why we're choosing this DE one is because it doesn't matter the fact that, yeah, so yeah, as we said, right, we choose D to E because it doesn't matter that E is not, or that D wasn't part of our set. We're going to choose it. So yes, the only adjacent vertex is D. E's edge to D is the least weighted, so we add it to our set. So we're doing this is we're looking at the least weighted of all the edges, which are, we're looking at all the vertices which are not in our set yet. Out of all of those, we choose the edge weight, which is the smallest. And so eventually they're going to bridge the gap, right? They have to bridge it. But actually, yeah, they could be chosen between 2 which are not part of our solution. So that's the idea, is we're going to choose E to D. And then we're going to choose B to D. So we exit the while loop and our MS2. So yeah. So yeah. Okay, so as I was mentioning, yeah, the most important, you do have to bridge the gap. Sorry, I got confused again. So I was right in the first place. This one didn't come green, so I was a little confused. But no, each time we do have to choose one, which like an edge which connects from what we've seen so far, what we haven't seen so far. And right here, that's B and D. So we choose that. And as you notice, like it's in this graph here chosen, but we didn't mark it as green. So I'm just going to use some green here so that I don't get confused again. So every single pass, we do have to choose something that's from one to the other. And so it's B to D. And then the only adjacent vertex is E. E's edge to D is the least weighted, so we choose that next. So hopefully that was clear. Sorry about the confusion. The picture here really confused me. I was a little bit off, but hopefully that makes sense. Basically, at each pass, you start at a random node at the beginning, and then at each pass, you're just choosing the smallest edge weight, which connects something you've seen before and something you haven't seen before, like something part of your set, something not part of your set. Until everything is part of your set. When it is, you have a minimum spanning tree. And this is the minimum, basically the minimum cost of sum of all the connections that you could possibly have in this graph. Okay, so that's prims. Yeah, so our set includes all vertices, so we exit the while loop and our MST is complete. So poll question, I'm gonna try and go kind of fast because we're kind of out of time now, almost. So I'll talk about crystals pretty quickly. So you can use Prim's algorithm to find the MS2 graph with which of the following properties? You can pause if you want. I'm gonna go over it. The answer is almost all these. It can be connected, it can be undirected, it can be, or it has to be connected. Yeah, undirected, it can be weighted, it can be cyclic. Sorry, yeah, so not directed because, yeah, it's just specifically prims, it deals with minimum spanning tree problem. Minimum spanning tree problem is undirected. Okay, so Kruskal's algorithm is a little bit different than prims, but it's all the same problem. And again, you're given a connected, weighted, and undirected graph, and it's going to give you an MST. minimum spanning tree. So it forms the minimum spanning tree by finding the least weighted edges that don't form cycles. So as opposed to prims, because prims was choosing between the set that you've seen so far and the set which you haven't seen so far. Crucibles does not care. It will choose between any two. As long as it's just not going to form cycles. So as long as the new edge doesn't form a cycle with the other edges you've chosen so far, it'll just choose the edge. And then if it does that, and until it can't do that anymore, then you're done. Because once it can choose a new edge and it forms a cycle, then it's not a tree anymore, right? So, yeah, and that's the idea, is it just always chooses the minimum edge, doesn't form a cycle. So the first thing it does is it creates an empty set of edges, and then it creates a list of the edges sorted by least weight. And that's really nice to have, sorting it first, because sorting it first allows us to just choose the smallest each time. And then we can decide, okay, should we choose this one? Will it form a cycle? And if it doesn't, then we can choose it, right? And if it does, because it's the smallest left, right? But or smallest we haven't chosen so far. But if it does form a cycle, we just skip it because we must have chosen something smaller already that already contains these vertices. So while all the vertices are not connected by the edges in our set, at the least weighted edge that does not form a cycle. The other edges in our set. And this is where union find comes into play, is right here. We use union find specifically for this problem here. We add the least weighted edge that doesn't form a cycle. And the reason why this is nice is because the way we ensure that there's not going to be a cycle, right, is the reason why we use union find is because if we have some vertex, right, already chosen, and like maybe there's something here, and maybe we have something like this already, right, and maybe all of these are chosen, and now, or maybe not chosen, we don't worry about choosing vertices and crystals, but maybe we've chosen all these edges. Now, what we would look at is we'd say, okay, well, what we do with vertices is when we originally put C and D together, we first made a set that contains C and D. So we put C and D together. And then when we include B in it, we actually put B in the same set. Like we union these sets together, for example. So any of these are the only set things in our set so far, right? We put B into the set. And then we basically are going to look at B and we're like, okay, we're going to look at this one, for example. And I'm just assuming that these are all the smallest. So maybe these are like all 1 for some reason, instead of the values they are, and maybe this one's like 2. So these would be the first ones we count. But when this happens, we have C, D, and B, we would not want to choose this because it would mean a cycle. And the way we decide that there's a cycle is we would find, or we'd identify, right, whether C and B are in the same component. And we do that with union find. We'd find the component of B and find the component of C, recognize that they're the same. And so if they're from the same component, then putting an edge between them would form a cycle because they're already connected by some path. And if we connect them by another path, that must mean that there are two unique paths between two vertices. And anytime you have that, that's, well, actually another definition for a cycle. So just good to know. So that would mean a cycle. So we can actually use union find specifically for this. So it's kind of interesting. So that's why we know not to choose it. But okay, that's the idea. And maybe that's kind of confusing. Hopefully it makes sense. And again, if you have questions, always message me. But let's go through this example. We create a list of edges and we sort them by the least weight. And our set so far, we choose AB. And then we look at CB. CB, again, not a cycle, so we choose it. We look at DE. DE doesn't form a cycle, so we choose that. We look at AC. AC does form a cycle. We would know that from our finds. Yeah, so we don't add AC, but we do add BD because it's the next one that doesn't form a cycle. And then we look at BE. Well, actually, I think we're actually done already. Yeah, but we could go through all the rest of them. And yeah, all of them are connected, so we don't need to worry about it. So we don't actually look at the rest of the edges. So yeah, we get a connected tree, minimum spanning tree. And we know that this is minimum because any other edges we add would just, they're more expensive, right? They're larger cost. And so this is the minimum you can have. And we know also that it doesn't, like, it's not like, oh, could we have used fewer edges? Could we have used more edges? Because it's a tree, and in a tree, you always have, here, for example, it's 5 vertices, so you have 1, 2, 3, 4 edges. And for any tree of v vertices, the tree itself has v minus 1 edges. So by choosing the minimum edges, of course, right? That makes sense kind of intuitively, right? If we choose the v minus 1 smallest, or like the v minus 1 smallest that we possibly can, right? Then we're going to get the minimum spanning tree. So like with a tree, it's always the same number of edges. But that's the idea of crystals. Full question, what's the MST of the following graph? So you can pause and try and answer, running out of time. So I'll go over it now. The answer for this is 1, and the reason why is because we can actually use one of the algorithms, right? So let's just use crystals. So minimum so far, let's choose AB. Next smallest CB, doesn't form a cycle. Next smallest, this would form a cycle. This would not form a cycle, so we choose this one. Then we choose this one. And then we would not choose this, choose this. So AB, CB, BD, AE, and EF for this. Yeah, so wait, AE, EF, BD, CB, and AB. Yeah. So the first one. Okay. And that's all for that. But next, there is a collaborative question. So we're going to talk about that really quickly. Let me stop sharing for a minute. Let me bring it up. My video's being kind of slow. We're just going to talk about it really quickly because I don't have a lot of time for it. We're going to go over it though, just kind of briefly. Yep. I'll share my screen again. So in this problem, you're expected to implement crystals on an undirected simple graph and write a method that is part of a class that implements the graph as an adjacency matrix. Yeah, and so the idea is to print the sum of the minimum spanning tree. So you might need to add necessary methods to the graph API or redesign the graph API. So the input is the first line. And yeah, so our goal is to basically make the minimum spanning tree, right? So how might we do that? Well, let me share my screen. So the idea is, let's go back to our example, maybe that'll help us. First and foremost, right, we want to have, but we're going to make use of the union find. Making use of union find. The first thing we're going to do is we're actually going to have all the edges, we're going to sort them by their weight, right? So we sort the edges by their weight. And the next thing we do is then we're going to choose them one by one. And if we haven't chosen, first we're going to try and find, right? We're going to see if, okay, is this one in the same set? And oh, yeah, if you want to think about it a little more first before I keep going, you can go ahead and try and put it on your own. It's always a good approach. So sorry for not giving you a chance to do that. But yeah, you can go ahead and do that. Okay. And if you're back, we'll talk more. Yeah, so as I mentioned, right, maybe you want to see if you want to find, right, and see if they're in the same set, right, first of all. And if they're not, right, then that must mean that there's no edge between either of the two sets. And if there's no edge between either of these two sets, that kind of means that there's like some graph here and some graph here. They're not connected. And the graph could just be one node, doesn't matter. But if they're not connected, then you can absolutely choose some edge between them. And so actually it's kind of good to know, right? There's two graphs here, right? And the way that crystals works is that like, okay, if they're not in the same component, then like we're gonna want to choose some edge between them. So why not choose the minimum one of all? And that's exactly what it does. Even if it's just two vertices, even if it's just a vertex each. And that's how crystals works. So that's kind of interesting to think about. But now we're gonna, if they're not part of the same component, then we're gonna, if neither of them is part of a set yet, we make a set of them, then we combine them with union. And then we keep going. Next smallest edge, we check they're part of the same component already. Like fine, just give me the same thing. Then we don't want to. We want to just like omit that edge. We want to skip over it. Otherwise, we're going to keep going. So let's look at some pseudocode for this. or if you want to try writing it before looking at it. Okay, using disjoint sets. So this is where we see why union find is so great for this problem. So you start with an empty set, and then for each vertex V, you make a set of it. So it's a set by itself. Then you sort the edges in non-decreasing order. So basically, yeah, you sort the edges by edge weight. And then for every edge taken in that order, so now in the sorted order, if they're part of the same set, if they're not part of the same set, right? So if find set of U and find set of V, then that must mean that they're part of different sets. So we want to choose the smallest edge which combines the sets. Well, that, because it's already sorted, that is literally the edge UV. So we take that edge, we include it, and we assign our set A, right, to be A. We add to our set A rather the edge UV, and then we union UV, because now those sets are combined, right? So we use union find, and we union here, we find the something. And now in the future, for example, if we were to get an edge between any two vertices and a vertex in U and a vertex in V set, well, now they're part of the same set because of how this union works. So when we do find set later, when you find set later, they're going to return that they're in the same set. So that's the way it goes. And then by the end, right, once we've gone through every edge, well, as long as there's a connected graph to begin with, we're going to get a connected graph for our tree. And that's it. And then we return it. Because everything, and once we have n-1 edges, we're not going to add any more because everything must be part of the same set at that point. So find set on any two vertices will give the same exact result. So this condition not equal will never be true once we found everything. And that is the idea of union find. So sorry for running a little long today. Hopefully it's covered a lot. You learned some stuff. You can try implementing this code, of course, if you want now. And if you have any questions, of course, message me. And thanks for listening, everyone. Have a nice day. Yeah, if you have questions, as you said, message resources. That's it. Bye, everyone.